Good morning, everybody. Let's start off with a couple announcements. The grader has finished grading homework 1, his sort of tentative first pass, so we'll post those in probably the next couple days as we go through that. He had some comments just in terms of like what would help him in the future, so if you guys could pay attention to these, it'll make his life easier and probably make it more consistent for your grading. The first comment was if you ever have a maple output that could be simplified, just try to run simplify command so you're not putting out a page of stuff. In some cases, that simplified command doesn't help and it doesn't actually reduce the amount of output. And that's fine, like you don't need to force it, but at least try to do that, and that should help. The second thing is he was noticing a lot of people are taking screenshots of your ease code and putting it in the document. That is not the preferred way to go because it's a little hard to see sometimes and it doesn't always reproduce correctly. So what you want to do is in ease, actually I'll show you how to do that if you haven't done it before. So in ease you'll want to print to PDF, and this is just the example from today. So what you do is make sure you solve first. Otherwise, if you don't solve first, it's going to output like question marks for your solution. And then just go to File, Print. And then you'll select the whatever PDF, maybe Microsoft Print to PDF or Adobe if you have it. And then you just want to choose the things that are relevant. So include the equations, include the solution, the main solution for sure. Probably don't include the arrays, and probably don't include parametric tables, and probably do include plots, right? So go through, configure that the right way, print it to PDF, and then attach that rather than taking screenshots, okay? That was comment number 2. Comment number 3 is make sure that when you're doing plotting, you're labeling the curves that you include, and I think you're getting, learning how to do all this stuff you need to do in Python and ease, so we'll give you kind of a pass on this one, but in the future you need to label everything that's in a plot. So that means if you're doing this in Python, you would do something like the plt.plot. You just need to include a label, right? So label equals the thing you want to call it. And then after you set up all your plots, you'd say plot.legend is true. So it'll take the label that you put here and then add it in a legend. So make sure you're doing that. If stuff isn't labeled in the future, it probably would be a point deduction because we don't really know how to grade that. So yeah, I guess that was it for announcements there. Anybody have questions on the upcoming homework before we get into it? Okay, we do have office hours after this, so we can hang around for that and ask questions there too. All right, let's pick up where we left off last time. If you remember, let me just actually skip back a couple slides here. So if you remember, what we were trying to do is we have our numerical solution. And in the numerical solution, one of the advantages of using a numerical technique is that you can be flexible, right? You can accommodate a lot of things that normally you couldn't easily accommodate in an analytical solution. One of those things is temperature-dependent properties. So despite the fact that you're doing that for your homework, analytically, you can also do it numerically. So we went through this example of coming up with a set of equations, just showing how you'd take the properties that are temperature dependent. So in this case now conductivity is temperature dependent and electrical resistivity is temperature dependent. And we just modify the set of equations that we have for every single node in order to capture that dependence, that functional dependence. I kind of went through incompletely how to actually implement all that stuff. So what I want to do to start today is go back through and be a little bit more careful talking through the steps that you would use to do that with these different techniques. So the first one that we started to talk about was just the ease technique. So we're going to take our current lead file that we had before from previous lecture and show how to just implement it in ease. And as you'd guess, it's really straightforward. So here's our ease program. This all here was exactly the same as it appeared before for this current lead example. internal nodes, node 1 and node n. That's where we're making our changes. You'll also notice up at the top of the file, we've got some new stuff here. There's these functions. So in ease, you can define a function, obviously. And what you need to do to define a function is you say my function and then the name of the function. So here we're calling it row underscore e. And then you pass as an argument the thing that you want to go into the function. So the only thing that this function can see is what's being passed into it. So if you wanted to include other constants that are part of the geometry, you'd need to add those as arguments to that function. Otherwise, the function it's like its own little container, right? It can't see the rest of the program. So you define the function. This particular function is only in terms of temperature. So we're safe just passing in temperature. We do that for both row E and for K. And then you have to assign a value to the name of the function. So here you have, we've called the function row E. So I have to give a value to something called row E inside that function. And it just returns that when it's evaluating. Okay, same thing here you can see for K. So what we've done down here now is we've taken our previous set of equations, and we just, every time you see K, now we're substituting in the function. This is a little hard to see, so let's do it this way. Right, every time you have what was previously just a constant conductivity, now we're calling conductivity as a function of some temperature. And we're evaluating that temperature based on the node. For these, it's node I minus 1. As we had set it up in the formulation. And here again, we're calling conductivity for I plus 1 average temperature. And then here we're calling resistivity function for the node temperature itself. So it's really simple to do this. There's kind of no trick to it. You just are putting in the temperatures. What you'll notice by looking at this, though, is we're solving for temperature. Temperature is included as an argument to this function. So this is a really highly implicit set of equations. Ease has no problem with that. It can deal with it. As we go to other solution techniques, we need to have explicit solutions for these. But for now, like, you just plug this into ease and it'll solve it. Right? So we can go and click solve. Solves it immediately. And we can look at our arrays. And we see our temperature solution. We could maybe look at the plot, and this should look maybe slightly different from the other one, although it's hard to tell, right? But we're getting a solution, and it looks valid. Again, if you wanted to make sure that you implemented this all correctly, you can go back here, and in this function, we could say, let me comment this out and say, row E is actually this original thing I had here. Oops, what did I do? Wow. Let's fix this here. So we would take the original value that we have here and just paste it in. And I'll have to comment this out again. And do the same thing for conductivity, and then it should return exactly the same solution that you had when it was not functionally dependent, right? This is a great way to make sure you didn't mess up, like, implementing the function or whatever. Like, it's taking out that entire temperature dependence, and it's just a great way of double checking. So that's how you'd approach doing that. Any questions on the ease part of it? Okay, makes sense.